Hello everyone. Today we are going to talk about our project titled as Probabilistic Seismic Facies Segmentation with Conditional Variational Autoencoders. The recent advancements in generative artificial intelligence have enabled the construction of complex image-based probability distributions through training models on data samples. Upon the completion of training phase, these probabilistic models are capable of generating very suitable outputs based on given inputs or the conditions. For instance, if prompted with the label dog, generative models can produce images of different dog breeds, which can be considered as samples from the original dog distribution. Since a generative model allows for multiple sampling, we can evaluate the statistical properties of approximated distribution, such as the mean and the variance. These statistical properties are informative for tasks requiring meticulous planning and quantification of uncertainties. In our project, we concentrate on the problem of seismic image segmentation. Our main objective is to generate multiple segmentation masks for a given seismic image using conditional variational autoencoders, and then finally assess the statistical characteristics of the segmentation process.
As our seismic segmentation dataset, we are using the 3D geological model of the Netherlands F3 block. The F3 block dataset encompasses a 3D seismic survey covering an area of 16 kilometers by 24 kilometers, located in the North Sea. This survey is rich in geological features and has been annotated to aid in seismic interpretation tasks. Regarding the segmentation classes, the dataset is annotated with multiple units. These units are vital for identifying different rock types and sedimentary environments, crucial for predicting potential hydrocarbon reservoirs. There are 7 segmentation classes. In the upper right plot, you can see the 3D model of the F3 block and segmentation classes with different colors. The dataset includes 2 primary views of seismic data: the inlines, which are horizontal slices through the seismic volume running east to west, crosslines, which are vertical slices running north to south. The dataset consists of over 600 inlines and 900 crosslines, each providing a unique cross-sectional view of the subsurface geology. In the upper right plot, you can see the configuration of inline and crossline slices in the 3D F3 block. In the below plot, you can see an example inline and crossband run through the segmentation map. The segmentation classes are represented as different colors. For efficient training purposes, we divided each of the inline and crossline slices to frames that are 64 by 64.
The conditional variational autoencoder has 2 main parts, the encoder and the decoder, where the latent space lies between them. The latent space is modeled as a normal distribution where the encoder learns to estimate its mean and variance from the training data. After that, we will sample some vectors from the latent space and concatenate it with the condition. The condition here is, as we can see in the bottom of the figure, is a seismic image which will pass through some convolution layers to obtain spatial information, and after that it will be concatenated with the latent vector. The output of this concatenation will pass through the decoder, and the decoder will generate the masks for this condition. The dimension of this condition and the latent space is carefully chosen in order to equally contribute to the decoder output. During the inference phase, we remove the encoder part and we sample directly from the latent space. We choose to sample 128 samples, and each sample will be concatenated with the same condition to generate multiple potential outputs for the same condition. After that, we will take the mean and the variance to get some idea about the uncertainty of the model.
Here's our result. We generated Gaussian distributions randomly 128 times for each image to calculate the posterior mean and posterior standard deviation. In the first example, you can see that our posterior mean, or our prediction, has successfully reconstructed the ground truth. Also, the standard deviation, or our uncertainty, is high around the boundaries of the segmentation. And the same goes for the second example. And the third example shows that our predictions are still not reconstructing well in complex images with more than 3 classes, and the uncertainty is also high where the model struggles. We calculated our posterior mean and standard deviation, and our standard deviation, which is uncertainties, can help inform about risky decision-making process. So overall, we reconstructed our ground truth well, but there still needs some feature work. For example, we will tune our hyperparameter. We will also add more layers in decoder. We will try to increase the image dimensions, and also we will explore the different architectures in variational autoencoders.